Let's talk about the average rate of change of a function. So suppose we have a quantity function which describes the number of mice that you have in your basement as a function of the number of weeks from the start of the year. So let's just suppose that on week 1, you had 4 mice in your basement. And then on week 5, you had 10 mice in the basement. So the question is, how fast is the number of mice increasing from week 1 to week 5? Well, if I was to draw a line between the point 1,4 and the point 510, we could calculate the slope of that line, and that would tell you how fast the number of mice is increasing. So let's calculate that slope. So you'll recall that the slope is the change in y over the change in x. Well, the change in y is 10 minus 4, or 6. So during that 4-week span, they got 6 more mice. And that was over a span of 4 weeks. So the slope of that line is 6 mice divided by 4 weeks, or 1.5 mice per week. Now, sometimes you want to leave that slope in a fraction because this can be easier to write a sentence to talk about the meaning. So this means that every 2 weeks, we get 3 more mice. You could talk about it this way: every week you get 1.5 more mice. That doesn't sound quite as nice. So let's write down this sentence. And the slope of this line between the 2 points is the average rate of change for that section of the graph. So 1.5 mice per week is the average rate of change of the function from week 1 to week 5. And what you'll notice is that the average rate of change is going to be different for different regions of the graph. So which is increasing faster, this section here from 1 to 5, or this section here from 5 to 10? If you guessed 1 to 5, you guessed correctly. Let me write that down. So the mice are increasing faster from week 1 to week 5 than they are from week 5 to week 10. So if you were describing this function, you would say the number of mice is increasing slower. All right, let's talk about the definition of this line. It has a special name. So you may recall from your geometry class, when you had a circle and a line that only touched it in one place, that was called the tangent line. So tangent means to touch. Secant line is a line that cuts across. So secant is to cut. So when we're talking about the average rate of change, we're looking at the slope of the secant line. Let me write that down for you. Right, the slope of the secant line between any 2 points of a function is the average rate of change for that part of the function. So let's try another example. Can you find the average rate of change from week 3 to week 9? And I would recommend hitting the pause button and trying this one on your own. All right, I would start by looking at the 2 points. And then you can draw the secant line and look at that slope. Is that going to be a positive number or a negative number? We calculate the change in y and divide it by the change in x. So on week 3, there were about 100 frogs in the pond. On week 9, there were about 250 frogs in the pond. So the slope of the secant line is going to be 150 divided by 6, and that's frogs per week, which is 25. Don't forget the units. And then let's write this in a sentence. So you have to name your interval because, as you can see, this is not a linear function. If it was linear, the average rate of change would just be the slope, and it would be the same for the entire function. But because this is nonlinear, the average rate of change is changing every section. So we could say from week 3 to week 9, the pond got 25 more frogs each week. Let me write that down. And then just for fun, you could look at the whole graph and say, is the average rate of change increasing or decreasing? So from 3 to 9, this would be your average rate of change. But like for the next section of the graph, is the average rate of change going to be faster or slower? If you said faster, you would be correct. So the number of frogs in the pond is increasing faster. All right, let's do another one. All right, let's do one where you're given an explicit function. The number of bugs in your yard in days since the start of spring is given by f of x is 0.2x squared plus 3x plus 20, where x is the number of days and f of x is the total number of bugs. Find the average rate of change from day 0 to day 10. And if I were you, I would hit pause and try this one on your own. So we need the slope of the secant line between those 2 points. So that's going to be my function evaluated at 10 minus my function evaluated at 0 divided by 10 minus 0. And don't forget your units. This is the number of bugs, and this is the number of days. So my average rate of change is going to be bugs per day. I plug 0 in. On day 0, there are 20 bugs. And we plug in 10. day 10, there are 70 bugs. So my slope is going to be 70 minus 20 divided by 10 minus 0. And that works out to be 5 bugs per day. Would you practice writing that in the form of a sentence? It's a really good idea, practicing writing it out in a very clear, easy to understand sentence. All right, so from day 0 to day 10, the number of bugs was increasing at the average rate of 5 bugs per day. Let's try another. All right, suppose you notice that you have a whole lot of ants in your kitchen, so you put out some ant traps. And this is the function which describes the number of ants in the kitchen since you put out the trap. Can you find the average rate of change from day 3 to day 5? I would hit pause and try this one on your own. All right, so evaluate the function at 3 and at 5, and the average rate of change is the slope of that secant line. So that's just f of 5 minus f of 3 divided by 5 minus 3. Don't forget the units. We end up with negative 20 ants per day. And looking at it, that should be no surprise because this is a linear function. So the average rate of change of that function is going to be the same for all of x, because the average rate of change is just the slope of the secant line between any 2 points. So the slope of the line is the same as the slope of the secant line when you have a linear function. So this function is decreasing at a constant rate. And that constant rate of change is the slope of the line. All right, let's do another. All right, let's look at this example. This is the number of apples on your tree. And what do you think is the average rate of change from day 10 to day 50? So that's just going to be the slope of the secant line between day 10 and day 50. And because that's a horizontal line, the slope is 0. So you can see that the number of apples changed a lot over that period of time, but the average rate of change is 0. All right, let's look at another example. All right, let's derive the average rate of change formula between 2 points on a function. So let's start with f of x. At this point, x, and I'm going to go a little farther down the graph, and let's say we want to make that a distance of h so that we can change it. So this would point would be x, and this point would be x plus h, and the point on the function would be x plus h and f of x plus h. And to find the slope of that secant line, we're going to find the change in y, which is f of x plus h minus f of x divided by x plus h minus x. Well, x plus h minus x simplifies to just h, I'm sorry. Because x minus x is 0. So now we can find the average rate of change, and we can vary the size of our interval. Let's do an example like that. So let's remember that this formula is the slope of the secant line between a point x, f of x, and a point a little bit farther down the function, x plus h, f of x plus h. And that slope of the secant line is the average rate of change of the function between those 2 points. All right, let's do another example. All right, let's let f of x be x squared plus 3. Can you find the average rate of change between the point x, f of x, and the point x plus h, f of x plus h? I would hit pause and try this one on your own. All right, so this is our average rate of change formula. So f of x is just x squared plus 3. To find f of x plus h, we just put x plus h where you see x squared. So the average rate of change is just x plus h squared plus 3 minus, I'm going to use parentheses because there's more than one term, all over h. Well, let me draw a little picture over here so that we don't forget that this is the slope of a secant line on this function between any point x and a point close to it, x plus h. So let's just simplify this. And x squared plus 2xh plus h squared plus 3. Let's distribute that minus sign. So x squared minus x squared is equal to 0. 3 minus 3 is equal to 0. And we'll notice that each of these terms has an h in it. We can factor out that h. H over h is equal to 1. So the average rate of change between any 2 points on the function is 2x plus h, the distance between the 2 points. Let me draw another picture here. All right, so let's talk about an idea from calculus, which is coming up soon in your math feature. So in differential calculus, we look at a function. If we look at any function that's continuous and a small enough interval, then that function looks like a line, and we can find the slope of that line. So the idea is that we're finding the average rate of change for a smaller and smaller interval until that interval is infinitesimally small. So that means h would be going to 0. And the slope of that line for this particular function is going to be 2x. And that's called the derivative, and they use the notation f prime. So if you wanted to know the instantaneous rate of change at a particular point, say 3, then we could find that easily. 2 times 3 is 6. So that would be the slope of that function at that particular point. All right, so that's where you're headed with the average rate of change. You're going to use it to find the instantaneous rate of change of a function. Let's look at our previous picture. All right, the average rate of change is the slope of the secant line between 2 points. Once that line becomes infinitesimally small, then it's going to be a tangent line, and the slope of that line is the instantaneous rate of change. All right, he'll talk about that next semester. All right, that's it.